Hello everyone, my name is Zijing Chen.
Hello everyone, my name is Jongwin. Thank you for listening.
We are Team 5. Our topic is about pattern matching. I'm gonna introduce you about pattern matching and I will talk about three algorithms about it. The first one is brute force. Second one is neural path, as known as KMP. The third one is Robin Cap. Let's start our presentation about pattern matching and its applications. What is pattern matching? Pattern matching is the process of checking whether a specific sequence of characters, tokens, data exists among the given data. Pattern matching is used to determine whether source files of high-level language are syntactically correct. It's also used to find and replace a matching pattern in a text or code with another text or code. Any applications that support such functionality use pattern matching in one way or another. For example, database schema and network systems. Pattern matching is widely used in our daily life, like the search engines we use as Google, and we also use Ctrl F to search in text. In more advanced example, we will search image in Google or Amazon. Let's talk about pattern matching algorithms category. We will focus on string matching algorithm. There are two types of string matching algorithm. One is exact string matching algorithm. It's to find one, several, or all occurrence of defined string pattern in a large string, text, or sequence such that each matching is perfect. All alphabet of the pattern must be matched to corresponding matrix subsequence. You can see from this picture, we will find the pattern AAB and we need to find the exact one AAB in the text. Another type is approximate string matching algorithm. Approximate string matching algorithm, as known as fuzzy string matching, search for substring of the input string. See that we will have a misspell here, but we don't want to find the exact misspell. We will to replace the correct word to a misspell. In more detail, there are four categories in exact string matching: character comparison, surface automata, big comparison, and hashing. Character comparisons compare character in the string and the pattern. The well-known algorithms are brute force algorithm, neural path algorithm, as known as KMP, and Breuer-Moore algorithm. We will talk about brute force algorithms and KMP algorithms in more detail. A surface automata uses the surface automaton's data structure that recognizes all the surface of the pattern. A well-known algorithm is reverse factor algorithm. Big parallelisms use the intrinsic parallelisms of the big manipulations inside computer words to perform many operations in parallel. Well-known algorithms are shift-OR algorithm, backward non-deterministic matching algorithm. Hashing. Hashing provides a simple method to avoid quadratic number of character comparisons in most probabilistic situations. Well-known algorithm is Robin Cap algorithm. We will talk about it in more detail. Now, let's talk about brute force algorithm. Brute force algorithms is a naive algorithm which use character comparisons. It slides the pattern over text one by one and checks for a match. If a match is found, then slide by one again to check for a subsequent match. However, its worst case is O of n times m, where n is the length of the string and m is the length of the pattern. It's not efficient. We will use this algorithm virtualizer to see how brute force algorithm is work. We will start over here as our beginning. First is we select the first character of the string and then compare with the first character of the pattern. If they match, then we move to the next character. If it's still matching, we will continue until it finds the first mismatch. If it's found the first mismatch, we will move our starting point to the next character of the string. Then click Continue to find the next matching. Okay, here's our algorithms. Then let's try another one. Then you will see the problem with the brute force algorithms. First, we start here. We go all the way to the last one. Everything's matching but until the last one. But if it's not matching, then we need to start over to here. However, we already checked each matching from 0 all the way to 6. Even though we had done all those matching, we still need to go back to start from the second to the first one. That's why our brute force algorithm is not efficient because it takes a lot of repeating steps. We know how brute force algorithms work. Then we can write a procedural code for it. It's very simple. Basically, just two loops. One loop for look over the character in the text, and another loop for look over the character in the pattern. If we find a match, then we return the index. If not, we return -1. The second algorithm is no-more path algorithm. It's the first linear time pattern matching algorithm. It uses character comparisons as well. The idea is to avoid repeated steps by keep moving forward in the text without backtracking. We will take advantage of the information that we know about the pattern to avoid matching the character that we know will match anyway. The worst case of this is O of m plus n, which is linear time, is very efficient. We will see an animation of the KMP algorithm and see how it reduces the time. We will see what it means to keep moving forwards on the string. We see that when you find mismatch on index 3, we won't go back to the beginning string that we start at 0. It will keep continue on the index 4 throughout the whole algorithm. You see that we had avoiding the repeated step like the brute force algorithms had done to only one time go through the string. It reduced the time very quick, but however, it might lead to a problem. As we can see here is one of the matching string, but we will have another one is over here. Then we will have an overlap character in index 7 and 8. If we keep moving forward in index when we find a matching string of purple and keep moving forward, we will miss the matching string for orange. Now we need to consider this problem and solve it. How are we going to solve it? And we're going to build a table with the pattern that we find the prefix that match with the surface. If we find that, then we will see that the prefix is matching to the surface. Instead of going back to the beginning, we will match in the second index because we know that the first two index is matching. Let's see what's that mean for a prefix, also a surface. We will take this substring because we need at least two characters to check a prefix and a surface. So a prefix of this substring is A, a surface is B, which is not matching. Then we will add another one when it's C. So the prefix is A, the surface is C, or it can also be A, B, and B, C, which is still not matching, and another one, F. Then here is F, C, F, A, B, C, or B, C, F. This is still not matching, and another one. Here is A, In A, we find that where the prefix is also a suffix. And is there more? Let's see. Well, it's no. A, B, C, F, and B, C, F, A. So we only found one prefix that is also a suffix. So we increase the index here to 1. Now we add another character, B, right here. Then we have A, B, A, B, A, B. We found it. So this one will increase to 2. Let's see the code. Here increase to 1. Here increase to 2. Let's see another example. Okay, here is 1. Here is 2 because here is a prefix, this is a suffix. Here is 3 because this is the prefix, this is the suffix. We want to find the longest prefix and the longest suffix. And when we go to B, it's not matched, then we go back to the beginning. Then where's A here, and it's matching to A here. When 2A here is matching to 2A here. When 3A's here is matching to 3A's here. So here is our table. Now we have the prefix table ready. Let's see how the algorithms work. We will start at the index 0 and compare. We will find until our first mismatch. Mismatch happens in index 3. And when we at index 3, we find a mismatch. That means that all the matching before are matched. So we will see that what it suggests in index 2, it suggests that we need to go back to index 0. Then we go back to index 0 and then move to the next character in the string. Okay, where is the next character in the string and in the pattern? We see that it's matched. Then we go to the next one, and then we found the first match. Then when we get to here, it says that we find the matching in B. Then we see what it suggests. It suggests us go to index 2. Then we will go to index 2 as C. And then before we stop at index 8, where we find our first matching, then we're at index 9. Index 9, and we see that it's a match. Then we will continue, and we find a second match. Now let's talk about the KMP's pseudocode. We use a pi array to collect the information for the table. And we will go through the pattern one by one to look for the longer prefix that is also a suffix, and then put all those information to the pi array. Now we have the pi array ready. Then we will go through the string. We will keep moving forward and not going back. And then we will check each character in the pattern. If it's a match, if it's not matched, we will want to know did we go back to the beginning of the pattern or somewhere in the middle. If we find a match, then we want to check the character at next character. And then if we find all of the characters match, then we will print out find, and then we will want to look for another match. Then we need to know in the pattern, do we need to go to the beginning or we go to middle of somewhere. The last algorithm we will talk about is RobanCap algorithm. RobanCap algorithm uses a hash function. It avoids number of character comparisons by only checking the substring that had the same hash value with the pattern. If the hash value match, then it will start matching the individual character. The average case is linear, which is O of m plus m. The worst case will be quadratic, which is O of m times m if you use a very small hash number. We will see an animation about the Robin-Cap algorithm. We will use a very simple hash function to show how Robin-Cap algorithms work. Assign a number to each character like 1, 2, 3, 6. We will find the hash value for the pattern. We just simply do summation. The hash value of the pattern is 15. Then we will have a window with the same size of the pattern to look for the hash value of the string. So the first hash value of the window is 12, which is not matched. Then we will slide to a next windows. The next window is 17, which is not matched. Then we will slide to the next one. Still not matching, we will slide to the next one. Okay, here we find that this hash value of this window is 15. It's matched the hash function. Then we will need to compare the character inside. Okay, we find the match. Then we need to find the individual character. Okay, individual character is matching. Then we slide to the next one. When we slide to the next one, we will continue to see that it's still not matching until you find the next matching hash value. When you find the matching hash value, you will do the same thing. Let's talk about the protocol of the Robin-Cap algorithm. Here, D is a number of characters. We had 256. Q is a prime number. We will use 11. So that our hash number will be very big, then we will have an efficient algorithm. P is the hash value for the pattern, and T0 is the hash value for the first window. And here is the pre-processing that we calculate the hash value for the pattern and the hash value for the first window. And after we have prepared that, we will do the match. If it match, then it will compare each character individually. If it's not, then we will need to slide to the another windows. So you can see from here, we slide to another window. But how are we going to do it? So instead of calculate the whole window again, we can just simply minus the first character and then plus the next character in here. And we will keep doing the same thing. When to the next window, then we will minus the value for the first character and then add the next character. So we have finished all the algorithm. Let's see a summary. So we know that the naive algorithm is very simple. That's why the runtime is very big. It's a quadratic. And we know that an improvement for the naive algorithm is the KMP algorithm. It's the first linear algorithm, so the runtime is linear. For Robin-Cap, it can reduce the multiple character comparison, and its runtime usually is very good unless you use a very small hash value.
Hello everyone, welcome. Today I will present the natural language processing, which is also known as parsing intrusion detection system. Along with that, I will show some demo using the AMTLR tool to construct a parse tree and a functional programming language Haskell to do the pattern matching programming. First, what is parsing? Parsing is a technique to break down a sentence into words to find out the grammatical types and syntactic relation. We have the parsing process look like this. We will have the sentence, then we can decompose the sentence into tokens. Then we will tag the part of speech to each token. There are 8 types of English words. They are conjunction, verb, interjection, adjective, nouns, pronouns, adverb, and article. Each word in English will be assigned to the syntactic behavior, but there are some cases. One word may have multiple parts of speech. It is called the ambiguity. To deal with the ambiguity, we come up with the English grammar rules. For example, we have the sentence can be paired into the noun phrase and verb phrase. The noun phrase can be paired into the article and noun. So far and so on, we have more grammar rules. Act like the patterns in English. We have two approaches for the parsing. The first one called top parsing. It is known as the expansion process, which begins with the root, then advance by applying left-hand side reduction. The strategy is top-down, left to right, and backtracking. We will go with this example. To analyze this sentence, we will use the first grammar rules. Then we expand the tree by applying more grammar rules. However, we realize that we cannot match any terminals here with the word choice or is. Then we may go in the wrong way. We do backtracking and apply another grammar rules and keep expanding the trees and tag the substring to the terminal. However, the verb is either auxiliary verb, but we don't have any the terminal for the auxiliary verb in the between. So we may want to do the backtracking to the node root s to apply another grammar rule that consists of the auxiliary verb. We keep expanding the trees and tag the substring to each terminal to complete the tree. For the bottom up, the second approach is bottom up. It starts with the words of input and build the tree up to the root cover on the input. This is the data directed search. It can reduce the string of tokens by inverting the reductions. For example, we write down the sentence into multiple tokens. Then we apply the right-hand side reduction form of the grammar rule to eventually build the tree up to the node root. In the next section, I will show how to use the ANTLR tool to construct a parse tree. ANTLR, short for another tool for language recognition. This is a powerful parser generator invented by a professor in University of San Francisco. This is used for reading, processing, executing, or translating the structured text. This tool can generate a parser that can build and work parse tree. Let's see how the program looks like. In the left column, we can specify the grammar rules and lexical to define the group that our token should belong to. In the middle column, this is how we can combine the program using Java. Then it will produce a parse tree like in the right column. We will try to use the tool to analyze this statement and construct the parse tree from this. In this demo, I will start with the built-in text editor to create a file called calculator.g4. G4 is the file type of the program. To save some time, I just paste in the code that I prepared previously. And you can see our program will start from the node root. The node root can be passed into the fraction or a new line. The fraction will also have the several parsing case to pair into an operator or another fraction. We also have the parsing rule for the operators. For lectures, it will define the group that our string token should belong to, and this lecture will be the input of our parsers. We will self-define. Then we will use this command to generate the necessary file. As you can see in the folder, the tool will generate some Java file for us. Then we will use the Java compiler to compile all of those files. Then we can start to run the program using this command. We will start from the node root and view. Now we can start to put in our statement. Let's try the statement that show in the slides. 7 minus 2, and we save it. So as you can see, the tool generate a parse tree for us from the statement we just put in. The numbers here will belong to the group erection, and the operator will belong to the Lexer group operators. The beautiful of this program is it's Java based, so we can incorporate those Java files to build a much more complex system. For example, if we want to pass the English grammar, we will need a few more grammar rules like this. I already have the program that can pass the English sentence based on the ANTOR tool. Let me show it here. This is the program. I will try to put in my English statement. And you can see this tool can correctly pass the English token into their part of speech. Try another example. So this is how the machine can understand our English language using the parsing technique. Next, let's watch the video to understand how the parsing technique is applied to the natural language processing using machine learning.
Analytics teams. Imagine you're searching a database of injury reports. You want to find lower body injuries. What do you search? Analysis from one large utility company showed that lower body injuries returned only a small number of results, far fewer than existed in reality. That's because their search tool was looking for the exact keywords, lower body injuries. But when the analysts used more specific search terms, like foot injuries, that returned many more results where foot was used in the context of distance. So while they had more results than searching for just lower body injuries, they weren't the results they wanted. This was because a foot can be both a body part and a unit of measurement. And while humans can determine context and know the difference, until recently, computers were largely stumped. Thanks to this field of AI, called natural language processing, computers can now analyze and understand textual data. In case you're curious, here's how natural language processing works at a high level. NLP algorithms can't read text like we do, but they can look for patterns, and they find these patterns by turning huge amounts of text into matrices. When analyzing text, the algorithm might first remove words that don't really offer us much value, stuff like a, the, is, and are. These are called stop words. Then the algorithm might split the sentences into groups of words and count how many times each group of words appears in each document and how many documents have that group of words out of all the documents being analyzed. Without knowing anything at all about the text, the algorithm can then tell how often a given word or phrase appears in a given document and how many documents contain that phrase out of all of the documents. So tokens that appear lots of times in lots of documents may not mean much, but tokens that appear frequently in only a few documents tell us that something's going on. For example,
Next, I will present about the intrusion detection system using pattern matching. What is IDS or intrusion detection system? This is the system that used to detect actions that attempt to compromise the integrity, confidentiality, and availability of the resources. It can be the device or software that can monitor a network or system. There are two approaches for the IDS. First one is the statistical method. Second one is the pattern matching technique. For the first IDS, the statistical intrusion detection is also known as the anomaly IDS. The statistical method will monitor the anomalies in the system, and this technique will look for the well pattern of the attack. This is the generic function of this IDS. The S will measure the anomaly value, but it is failed to understand the interrelation between the event. There are disadvantages of the anomaly IDS. First, it can suffer from the false positive, and the intruder can train the system over length of time to keep his activity under the threshold. By that way, he can avoid alerting the system, and it is hard to determine a threshold if it is the intrusion or not. The second IDS is called the pattern matching or mixed-use IDS. It can predict the next step of the intrusion by watching for the occurrence. It can determine intrusion by understanding the interrelation of the events. This equation here will calculate the probabilities if an activity is an intrusion or not. The AI value will measure different aspects of the system. The I value will be the hypothesis that the system is currently undergoing an intrusive attack. My teammate already talked about the approximate matching, so I'm gonna skip this part. The approximate matching is useful, but mixed-use IDS cannot be solved by using this pattern matching technique because it requires the matching of partial order, context-free, context-sensitive structures, and the matching has to be done in the region of time. So another system is able to model the attack. The intrusion signature will be partitioned into the set of orthogonal characteristics. They are linearity, unification, occurrence, beginning, and duration. For the linearity, this is the signature pattern has to follow a strict chain of the event with no conjunction or disjunction. For example, the token Y have to strictly follow the token X. For non-linearity, the partition can have partial order. Unification is we can instantiate the variable to earlier events and match this event to later occurring event. For example, we can store the event A and B in the value X, then we can access the A and B to the value X. Occurrence, the characteristics specify the ready replacement of time of the event with respect to the previous event. For example, we had event T2 here. It will start within 5 seconds from the event T1. Beginning can specify the absolute time of match of the beginning of pattern. Duration or constraint specify how long that event is active. To build the mixed-use IDS, we can use the color patronage to illustrate our approach. We will design a system that can alert the admin if the user do 4 forks login attempt. In this diagram, we will have 5 stages: initial stage, final stage, and the 3 stages in between will represent for the login attempt. This diagram in nature will have one stage transit to other stage in linear direction. So this is the fixed linearity. The unification is expressed through the global variable, and then we can calculate the duration by access those global variable. The occurrence, beginning, and duration are expressed through the goals here. The goal is the Boolean expression that it can be deconstructed if we satisfy the specific conditions. To understand more about it, let us examine how to consume this pattern. First, we will have the pointer in the beginning of the string. We will have the 2 circles in the initial stage. Then we consume the token A. This goal will be the construct because the condition A is satisfied. Similarly, we move to consume the token B and move to the red circle to the stage 3. For the next token A, we will move the green circle to the S5 stage. For the last stage, this goal requires at least one token from S5 and at least one token from S3. We can satisfy the condition, then we can deconstruct this goal and move the 2 circles into the final stage. In the last session, I will show how to use the pattern matching with Haskell. What is Haskell? Haskell is a purely functional programming language. We can define the type of the input and output like this, and we can write the function like this one. Haskell is also the statistical type. That means the type of the variable is determined at compile time. Similarly to other programming language, we have the type character, integers, and Boolean. This is how we write the factorial in Java. First, we need to initialize the variable. Then we can use the for loop to calculate the factorial of the number. Then we will reduce the output. To start with the program, we will first need to create a file called factorial.hs. HS is the file type Haskell. Then we can start to put in our code to calculate the factorial. We will start with the function name first, then define the inputs as an integers. The output is also an integers. The factorial of base case 0 will be equal 1. The factorial of any other number will equal to that number multiplied by factorial of previous number. So as you can see, we have two patterns here. The first pattern is factorial 0. The second pattern is the factorial of n, of number n. So this is all we have to do to write a factorial function in Haskell. It's much more simple than the function written in Java. We're gonna save this file and we call the Haskell CLI. Then we load the file we just created in. Now we can call the function to calculate the factorial of base case 0. It returns 1. This is the correct result. We will try with all the number. This is also the correct result. So we finished writing a factorial function in Haskell. I'm gonna show another demo using Haskell to calculate the sum of a list. If we are using Haskell, we will treat the list like a dog. It will have a head and the rest of the body. So Haskell use this pattern to define a list. We have x belong to the head and xx will be the rest. So to start with the demo, we will first start with create a file called sum.hs. Start with the function name sum. The input will be the list of integers. Then we will use this syntax to define the list of integers and produce the output as also integers. The sum of empty list will equal 0, as you know. The sum of non-empty list will be described like this, equal to the head of the list plus the sum of the rest of the list. So if our list is empty, it will return 0. If our list is not empty, it will fall into the second pattern and then equal to the first number in the list plus the rest number in that list. This is similar to how we write the sum recursion function in Java, but in Haskell, it's much more simple because we can define the sum function and do all the calculation, do all the recursion calculation in just one line of code. We're gonna save this file and we call the Haskell CLI, load in the file we just created. Then we call the sum function and pass in an empty list. It returns 0, then we get the correct result. We try with the non-empty list. The result is also correct. So this is how we can write the sum function using Haskell and pattern matching. So I and my teammate already present multiple approach in pattern matching. We also talk about the application that pattern matching are applied to solve the real world problem. If you have any question, please leave it in the discussion forum and we're happy to answer them. Thank you for listening.